Alright, valence electrons and Bohr diagrams. So we've been looking at how the electrons are configured around an atom. They exist in certain energy levels, known are also called shells. But the most important ones are the valence electrons, the ones in the outer shell. This is also why we study Bohr diagrams, because they're very useful. Below is a Bohr diagram. So each circle, other than the inner one with around AL, represents a energy level. So the innermost energy level 1, can have at most 2. The second energy level can have 8. And then the next energy level, I think, is 18. Yeah. But we see only 3 for aluminum. So atoms have a nucleus that contains protons and neutrons. Electrons are contained in shells, also called energy levels, that surround the nucleus. An atom is made up of mostly empty space. Protons have a positive charge, electrons have a negative charge, and neutrons are neutral. So each electron shell or energy level can hold a certain number of electrons. Electrons shells are filled from inside out. So even though Aufbau rule, the Aufbau rule tells you what the configuration is going to be, it states that it's filled in terms of lowest energy level or energy. And even though we do, for example, 4s before 3d, the 3d is actually going to be filled before the 4s. It makes no difference though, because we mostly are only going to look at the highest energy levels. So noble gases have a full outer electron shell, and I should indicate that the word full doesn't mean this max number. We'll see in a little bit what that specifically means. So all other elements have partially filled outer electron shells. I will tell you that a full outer shell is just 8. That number seems off. Why is it? That's not right. It should be 2 and 2. 3 should be 18. 4 should be 32. And so on. Should be this. I need to change this PowerPoint. Why is that PowerPoint on? So the electrons in the outermost electron shell are called valence electrons. Don't copy this table down. I think it's wrong. But electrons in the outermost energy level or electron shell are called valence electrons. The shell containing electrons that is farthest from the nucleus is called the valence shell. The number of electron shells with electrons is the same as the period number. So, getting let's look at the periodic table. So here's a periodic table. The columns see if I can actually find it. They're called groups. And the rows are called periods. So the energy level is going to be the same as the number for the periods. The highest energy level is going to be determined by what row it's on. So for example, the highest energy level for hydrogen is 1. Highest energy level for copper is 4, because it's 4s2, 3d9. Noble gases are usually unreactive. This is because they have a, and here's this word again, full valence shell. And an element with a full valence shell is a happy element. For two atoms to join together, they must gain, lose, or share electrons in order to complete a full valence shell. Elements with a full valence shell do not easily gain or lose electrons. So the noble gases are the most stable elements. They do not like to react because they cannot gain any more valence electrons. Everyone good? So atoms want to gain stability. Atoms will try to gain or lose electrons to have a full valence shell. Metals usually try to lose electrons, and nonmetals usually try to gain electrons. Electrons are negatively charged. Don't need me to go back to say something. Protons are positively charged, and neutral atoms do not have a charge because they have the same number of protons as the same number of electrons. When atoms gain or lose electrons, they become either positively charged as they gain, or as they lose, and negatively charged as they gain electrons. An atom with a charge is called an ion. So if you've gained an electron or lost an electron, it's become an ion. Bohr model is very useful in helping to visualize how the electrons on the highest energy level is going to be shared. It will also help you in doing something called a Lewis dot diagram. So the very first image here was the Bohr model. That's the Bohr model. But for the most part, we only concern ourselves with the highest energy level, the outer circle. I'm trying to see which PowerPoint has this definition on it. Which I don't see. I could have swore that this one had it. Let's go look it up. I can't find the PowerPoint. So, the octet rule. The octet rule refers to the tendency of atoms to prefer to have a full valence shell. Because of the order of the electron configuration, because of how the periodic table is shaped and how we fill it up, a full valence shell is just 8 electrons. So every atom, according to this octet rule, wants to have a valence shell with 8 electrons. All atoms want to have 8 electrons on the outermost energy level, or outer shell. Atoms with fewer than 8 electrons tend to react and form more stable compounds. So valence electrons are defined as electrons in the outermost orbital. These electrons are the most important because they are the only electrons involved in chemical bonding. These are the electrons that are not in the outermost shell are called core electrons. And core electrons do not really interact when reactions go on. It's just the valence electrons that do all chemistry. What the core electron, really what the protons, neutrons, and electrons overall do is determine whether or not something will react. But if you know two things will react, it only deals with valence electrons. So if you know that if you put two chemicals together and you know they react, all you need to know is what the valence electrons on the two chemicals are, and that will tell you how they will react. If they will react is outside the scope of this class. We don't know if two things will react because that depends on the strength of the charges between the positive nucleus, the core electrons, and so forth. But if we do know that two chemicals will react, then all we need to know is what the valence electrons are. So if you sort this by increasing energy levels, the core, really you don't have to. Some people sort this, so like this. This is unsorted. Sometimes you'll see it sorted where the 4s is grouped with all the other 4s. But the core electrons is anything less than the highest energy level. The valence electrons are the ones that are on the highest energy levels. So here, when you write the electron configuration out, the highest energy level is 4. So this element has 6 valence electrons. And it has 28 core electrons. What element is this also? Now you can count up all the numbers, or you can just look at 4p4. Yes, selenium. So how many valence electrons are in the following atoms? And I'm just going to switch over to notebook paper. So helium. What is the electron configuration for helium? So what is the number of valence electrons? 2 valence electrons. So the highest energy level is 1. There's 2 here. I should also note hydrogen and helium are exceptions to octet rule. Yeah. So looking at the periodic table, so for selenium for noble electron configuration, we look back, we go up a row and go to argon. And we write down the previous noble gas. And then we just read off the row. So this would be 4s2, 3d10, and 4s4, and 4p4. Yes.
One last call for picture retake. If you need your picture for the yearbook retaken, you may go down to the board.
So this was for selenium. You basically replace the 1s2, 2s2, 2ps by doing that. That was from, I just know from that diagram I gave you where it showed that this was 4s and this is 3d, and then you just read off the row. You start with this row for selenium. So you basically, you take this and then you just read the row, and that's it. So helium and hydrogen are exceptions to the octet rule. They only require 2 electrons to be full. Everything else requires 8. Alright, so let's look now at oxygen. What's the Lewis dot for oxygen? So 1s2. This is the diagram I'm looking for. So oxygen is right here. So 1s2, 2s2, and then 2p4. So how many valence electrons does it have? 10. So the highest energy level is 2. So we only look at these. So it has, how many did you say? 6. We only look at the electrons on the highest energy level. Let's do sulfur. So sulfur is 1s2, 2s2, 2p6, so reading off every row, then 3s2, and the sulfur is right here, which would be 3p4. So this whole column is p4s. So highest energy level is 3. So we only look at these 2, so that's another 6 valence electrons. Let's do the one below it, selenium. You've already done that. Let's look back at it. Selenium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. It has 6 valence electrons. Y'all notice a pattern? Y'all notice a pattern for selenium has 6. What do you think? What do you think tellurium would be? The one right below selenium. 6. Alright, let's do sodium. So sodium is right here. So it's 1s2, 2s2, 2p6, and it's going to be 3s, and this is the first one, that's the second one, so it'll be 3s1. Highest energy level is 3, so it has 1 valence electron. Let's do potassium right below it. So 1s2, 2s2, 2p6, 3s2, come over here, 3p6, and it's 4s1. Highest energy level is 4, so we choose and add up all the 4s. There's only 1. What do you think rubidium is going to be? Rubidium is right below, right here. What do you think? How many valence electrons do you think rubidium is going to have? 1. So looking at your periodic table, all of these have 1 valence electron. All of these have 2. Skip the transition metals. All of these have 3. All of these have 4. All of these have 5. Oxygen all have 6. These have 7. These have 8, except for helium that only has 2. So a nice little trick to, instead of having to write out the full electron configuration, to determine how many electrons are going to be on the outer shell, we have a very nice way of figuring that out. So how many valence electrons does chlorine have? 7. So if you were giving the electron configuration, how many electrons are in the valence shell for this one? 8. So this has a noble gas. So that's a noble gas. Or at least has a noble gas configuration. It's stable. How many is in this? 6. So we're only looking at the highest energy level, was this 4. So we have an S2 and a P4. 2 plus 4 is 6. And this is the noble gas configuration. We abbreviate the core ones, or the major core ones at least. So the highest energy level is going to be 5. So we have an S2 and a P2, the 5th energy level. So that's 4. And then here the highest energy level is 3. So this has valence electron 5. So the nice trick is using the periodic table. The first column is going to be 1, second column is 2, skip the transition metals and the special series at the bottom, and go to boron, that'll be 3, 4, 5, 6, 7, 8, and helium is an exception because it only can hold 2. This is something that you're going to have to memorize for the rest of the year and get down, because valence electrons is very, very important. So let's look at Lewis dot structure. Here they're calling it electron dot structure, but give credit to Lewis. This is called the Lewis dot structure. Lewis dot structure consists of the element symbol representing the nucleus, surrounded by dots representing the electrons, valence electrons. So basically, it's a very reduced Bohr model. And I will use the name Lewis dot, as I never really see electron dot. So let's figure out how to write Lewis dot structures. Carbon. How many valence electrons does carbon have? Four. And what's its symbol? Capital C. So we're going to put 4 dots around it. And I tend to prefer that you spread the dots out like this. Let's look at one that has a full so you can actually see the where they all go. Let's look at neon. So neon has a full, because it's a noble gas, full valence shell. Full means 8. Unless you're hydrogen or helium. Its symbol is He. So if you're putting 8 dots around it, you're going to put it, imagine it being a square around it, and 2 dots on each side. Let's do one with 6. Let's look at oxygen. Oxygen has 6 valence. So it doesn't matter how. So this is acceptable. So it's better to begin by putting 1 dot around it on each side before you start putting the other dots. This is acceptable. What you shouldn't do is this. So this has 6 dots, but I have a side without a dot. It's not preferred to do it. We try spreading it out. So let's look at magnesium, Mg. How many valence electrons do we have? 2. So I tend to prefer doing this. So this is the preferred. Again, we spread them out. Somewhat acceptable. To be like this. I don't prefer this. Spreading it out like this. I like keeping them kind of together. But it's alright. I'll accept it. What you shouldn't do is this. Is group them together on one side. I'll even cross that out. Either one of these are acceptable. Because it kind of makes sense to do this in some cases. What you shouldn't do is group them together initially. We'll see why. Because when we start bonding atoms together, having the dots far away from each other or by themselves is going to make it much easier. We will see later when we actually look at how atoms bond together. This would be a pair, and pairs can be by themselves. Lone electrons are bad. We do not want electrons by themselves. And what happens is that means something is going to come over here and fill these empty spots. I probably won't count wrong if you do this. I'm just getting you in the habit of being more acceptable in writing it. It's not technically wrong because all this is supposed to show is how many electrons. Anyway, when we start doing more advanced stuff with Lewis dot, we're going to be moving them together and around anyway when we combine atoms. So what would be the Lewis dot for this? So what would be the Lewis dot? So 1s2, 2s2, 2p3. Again, if you have the periodic table memorized, using this notation, you just have to look at the last one. So this is my p block. So it's in, this is your 2p's, your 3p's, and it is 2p3, so 1, 2, 3, this is nitrogen. That tells me it's nitrogen. Highest energy level tells me the number of valence electrons. So these are your valence electrons. So it has 5. 1, 2, 3, 4, 5. So what would this one be? Again, you can count up all the electrons to figure it out, but if you have the periodic table memorized, then we know it's going to be in the P block section. We know it's going to be the 4th period, or 4th row. And the 1 on the P tells you it's going to be the first one. So, row 4, we're looking at 4p1. This is your P's. 4p1 is right here. It's gallium. And gallium, we don't even need to count it up. We should know it's 3 to begin with. But even looking at, we have a 4s2 and a 4p1. That's 3. So it'd be gallium with 3 dots. This one, again, 5th row, 5th in the column for that P block. So 5th row, we're looking at indium, and aluminium, tellurium, and iodine. That would be iodine. Iodine has S2 and P5, 7, so it has 7 dots around it. This one, we're looking at the S blocks. So Ne3S2. Again, you could look and realize that neon has 10, and S2 has 2, so this would be the element 12, magnesium. Or you could just look at the 3rd row in the S block section and look at the 2nd one, magnesium. This will have 2 dots around it. So here's the Lewis dot for elements 3 through 10. Looking at the entire period. So I guess spacing them out on opposite sides, like beryllium, is alright. You'll notice that they tend to put, like for carbon, they tend to space the 4 dots evenly around. and they don't group until they have other 4. Make sense?